Good afternoon. In the last class, we have seen single layer feed forward neural networks. That is perceptron. The perceptron concept. Only single layer feed forward perceptron or neural network we have seen. And what is perceptron? Those things. Along with that, learning algorithm of the single layer perceptron. Those things we have seen in the last class. So in the today's session, we will see the multi-layer feed-forward neural networks or perceptrons. So in this multi-layer feed-forward neural networks, we can do little complex problems which are not solved by the single-layer perceptrons. Before going to that, what are the limitations of the single-layer perceptron? So if you see the limitations of the single-layer perceptron, the single-layer perceptron can only learn linear separable problems. So linear separable, non-linear separable. So if your vectors are linear, or the outcome of the corresponding perceptron is, as an example, we have seen table, chairs, beds. In that, if you want to separate into the two classes, we need to draw a single line between the two classes or a simple hyperplane between the two classes or two groups. That can be possible by using this single layer perceptron. So it is applicable to only linear separable problems. Only if you have chairs and tables, only two classes, then we can draw the line. But if you are having more than the two classes, then, or if it is non-linear group or section, then it is impossible to draw or separate the vectors or outcomes with single line or hyperplane. So which is not separable is nothing but it is not linearly separable with single line or hyperplane. So for example, if we take Boolean AND function is linear separable, whereas Boolean XOR function is non-linear separable, or it is not a linear separable XOR. So how means already we have seen anyway. So if you see that Boolean AND and Boolean XOR, so if you see that logic of the AND gate for the two input gate, if what are the combinations 0 0 0 1 1 0 1 1, so those things are represented here on x1 and x2 axis, which is x1 is one input, x2 is another input. So correspondingly your four combinations are represented on that quadrant. You see here, as per the AND logic gate, what is the corresponding output for these four combinations? 0 0 is 0, output is 0, 1 0 also 0, 1 1 is also 0, whereas 1 1 with AND logic gate it becomes 1, y becomes 1 or output becomes 1, right? So that means here 0 0 1 0 0 1 or comes into the one group which are not firing the corresponding neuron, whereas 1 1 combination will fire the neuron or it is in another class or group. So if you want to separate those two groups or classes, simply you can draw one line or hyperplane between these two classes, because below that hyperplane or dotted line, the group which belongs to the non-firing of the inputs or vectors. Above the dotted line, it causes the firing of the neuron. So these two groups are separated by this dotted line. That's why this Boolean AND is linearly separable problem, which can be possible with a single layer perceptron. That's why 1 1 is circled, whereas other inputs like 0 1 0 0 and 1 0 are not circled. Those are separate group, and which is circled with cross is circled means that is another group. Just to differentiate that. So if you see the non-linear separable problem, here again x1, x2 are the two inputs, and the two input XOR gate if you consider Boolean XOR gate with two inputs x1 and x2 if you consider. Again the possible input combinations are 0 0, 0 1, 1 0, 1 1. What are the corresponding logic gate outputs? XOR outputs is nothing but are for which combinations your output is 1, for which combinations your output is 0. That we know already, right? For XOR gate, if both the inputs are same means your output is 0. Both the input means both x1 and x2 is equal to either 0 or 1. Then your output is 0. If both the inputs are different means then your output is 1. That's why if you see here 0 0 as well as 1 1, both are circled. So those two will give the corresponding output as 0. That means that do not fire the corresponding neurons. Whereas 0 1 1 0 on x1 axis as well as x2 axis, 0 1 and 1 0 which are represented with only cross, the corresponding output is 1, which will fire the corresponding neuron. Again here also we are having two groups, one is firing group, another one is non-firing group or class. But here it is not possible to separate these two groups with linear line. That's why it is non-linear separable problem. It requires two lines to separate into the two groups. Just by drawing one single line, that bigger dotted line, if you see, if you draw that single dotted line, above the dotted line, bigger dotted line, you are having 1 1, which is in one class, let us assume. But what is the another point which belongs to the same group, like 0, like 1 1, that is nothing but 0 0. That also should come above that line or hyperplane. But it is impossible to bring that 0 0 point above that point. So obviously it requires two lines, or we should go for non-linear separation. So that's why with single layer perceptron it is not possible to draw the line between the two classes, or it is not possible to separate linearly. So to avoid these limitations, we need to go for multi-layer perceptrons. Okay. As a simple example, you see the perceptron limitations in that itself, a linear inseparable problem means, let us assume if you want to separate these problems and those points, simply those cross points, are different type of output vectors or outputs, and which is not which are having different groups, then how to separate that points? It requires many lines to separate that groups. So it is nothing but it is linear inseparable problem. You cannot draw a single line to separate that points into the two classes. So those are the limitations of the single layer perceptron. And in the multi-layer perceptron model or multi-layer feed-forward neural networks, so if you see one of the example or one of the function is nothing but credit assignment problem. Here that name itself suggests that credit assignment problem means we need to assign the credits if action is good or if it performs well. Otherwise, we need to blame the corresponding neuron. Or we need to appreciate means we are assigning the credit. We are not appreciating means we are blaming the corresponding neuron. But that name itself, it indicates that credit assignment problem means for if actions are good, we need to appreciate or we need to assign the credit. That credit assignment or that credit is indicated with a circle with arrow, down arrow, which are not circled, which arrows are not circled means those are nothing but blamed actions. So the bottom I represented for which actions we can give the credit and which actions we can give the blame to get the required outcome. The overall outcome is nothing but here represented with the outcome from the corresponding neuron. The circle represents the neuron. Let us assume from that neuron we are getting the overall output. The corresponding neuron has 5 inputs. So those 5 inputs are represented with the 5 input lines with arrows, right? 5 input lines towards that outcome or neuron. So in the each line again 5 down arrows are represented, right? Those down arrows are representing, those down arrows are indicated with, let us take the above line, first line. 5 down arrows are is doesn't mean it means that it means that those are the actions of the internal decisions of the first line, which are represented with A1 to A5, A1, A2, A3, A4, A5. 5 lines are there, that's why A1 to A5. On the second line, the corresponding internal actions are represented with B1, B2, B3, B4, B5, B1 to B5. Likewise, the last line, synoptic line or the last line, represent the corresponding internal actions with the down arrows, that is E1, E2, E3, E4 and E5. The corresponding outcomes which are going towards that neuron are represented with the O1, O2, O3, O4, O5, which are nothing but outcome of the internal decisions. If we take the O1 represents the outcome of the internal decisions 1. That means because of the internal actions of the first input line, the corresponding output is nothing but the O1. O1 is nothing but outcome of the internal decisions. The internal decisions means some are given with credit, some are not given with credit. Because of that credit assignment, we are getting the corresponding outcome O1. That is because of the internal decisions of the first line. Likewise, O2, O3, O4, O5. O5 is nothing but outcome of the internal decision, outcome due to the internal decisions of the fifth line. So, for what actions you are provided with the credit, what actions you are provided with the blame. Because of that actions, because of that credit assignments, your output will vary, and that will contribute towards the total outcome. So this credit assignment problem, generally it is a combination of two problems. Overall credit assignment problem or function need to perform with the two problems. One is structural credit assignment problem, another one is temporal credit assignment problem. So the structural credit assignment problem means because of that internal decisions, whether you need to assign a credit or blame. Let us take the same example, first line. In that first line, the down arrows are representing internal actions. That internal actions, among that internal actions, second one and fourth one are given with the circle, means it is given credit. Those actions are required to get the desired output. So that's why the second one, that is nothing but A2 and A4 are provided with the credit. So the corresponding output O1 is not given any credit. Whereas if you take the second line, B3 is given with credit and the corresponding O2 also circled, means that is temporal. The first one, on the line down arrows are represented with circle, means that is nothing but structural credit assignment problem. If you are identifying particular actions and if you are giving or if you are assigning some credits to that particular actions which are required, which are contributing towards the desired output, that is nothing but structural credit assignment problem. And from the actions of that internal decisions, whatever the outcomes you are getting, O1 to O5, again if you are providing some credits towards that outcomes of that outcomes due to that internal decisions, that becomes a temporal credit assignment problem. So here on the line, before going to the neuron, the corresponding output, two places we are assigning that credits. That's why internal actions, if you are assigning some credits towards that internal actions, means that is structural credit assignment problem. If you are assigning credits towards that outcomes due to the internal decisions O1, O2, O5, then that becomes a temporal credit assignment problem. By combining these two, we need to perform this credit assignment problem. So if you see here, in the first line, A2, A4 are assigned with the credit. In the second line, B3 is assigned with the credit. The third line, C2 and C4 is assigned with the credit, and so on. And in the last line, E4 is assigned with the credit. But those actions are good to get the desired output. That's why the credits were assigned, and the remaining actions were not assigned with the credit, means those are blame actions. That means what are the blame actions in the first line? A1, A3, A5 are the blame actions. Because of that credit assignment to the internal actions, the corresponding outputs are nothing but O1, O2, O3, O4, O5. So already we were assigned some credits towards that down arrows, right? Those are internal actions. So already we have completed that structural credit assignment problem. Now the next phase is temporal credit assignment. Now we need to assign that credits towards that outcomes of that internal decisions O1 to O5. Among these 5 outcomes, let us assume that I need to give credit only to O2, O4, O5. Remaining are blame actions. Even though that may blame actions means that may not contributing towards the desired output. So that's why O1, O3 are the blame actions, blame outcomes, and O2, O4, O5 are the were given with the credits. So this will contribute to, this will give the overall output of the outcome or output of the neuron. So this is all about the credit assignment problem. Hope understood. So as an overall, so if you see here, credit assignment problem consists of 2 problems. One is structural credit assignment, another one is temporal credit assignment. Structural credit assignments will be assigned for the credits will be assigned for the internal actions. So because of that internal actions, you are getting some outcomes O1 to O5, and again if you are assigning some credits towards that outcomes due to that internal actions, then that will become the temporal credit assignments. Then you will get the overall outcome of the neuron. So even though you are assigning some credits towards that structural credit assignment like A2, A4, that may or may not required output, that may be 0 output also. By providing the credits to the A2, A4, you are getting that 0 output. But which are actually contributing means only O2, O5, O4, O5 only contributing towards the desired output like this. So you can assign either credit or blame at any place, either at the internal actions or at the outputs. By combining these two only, credit assignment problem can be performed. So next, if we see, the next one is error correction learning rule. So here error correction, there are many learning rules. Among that, one is, when in the last class also we have seen one training algorithm. So here one is even single layer perceptron or neural network learning algorithm. One more learning algorithm is error correction learning rule, which is also called delta or Windrow-Hoff rule. So if you see the block diagram, let us take that input vector, or let us assume directly you can start from the output neuron K. You have output neuron K in the block diagram representation. We can represent like this. The output neuron K has, or it is giving an output which is nothing but actual output yk of n. Output neuron K is providing the actual output yk of n. So which has an input x of n, which is the output of one or more hidden layers or hidden neurons. Now x of n is the output of one or more hidden neurons. These hidden neurons are having the inputs from the input vector. Your actual output and the desired output dk of n at last. The dk of n is compared with the actual output, then that is nothing but dk of n minus yk of n will give some error ek of n. So if you are getting the desired output or actual output which is equal to the desired output, then error will be 0. But if desired output is not matching with the actual output, then it will present some error. Now that error is used to adjust the weights of the corresponding output neuron K. When we are leaving all the one or more hidden layers, only we are concentrating on the output neuron K weights. So by adjusting the output neuron weights, by using this ek of n error, you will get the either your actual output may increase or decrease to match with the desired output, so that your error need to be make towards 0. It should be close to 0. It is continuous process, like in the closed loop how we are performing. It is continuous process. There you can adjust the firing angle. Here you are adjusting the weights of the corresponding output neuron K. So this action is represented with the block diagram like this. This is nothing but error correction learning rule. This error correction learning rule, error is generated due to the difference between the desired output and actual output. That error adjusts the corresponding output neuron, corresponding weights of the output neuron K, so that the error need to be minimized. So this is the error correction learning rule. If you see the mathematical equations of this error correction learning rule or delta or Windrow-Hoff rule, the error at the neuron K is nothing but ek of n, right? The corresponding error is ek of n. Ek of n is equal to desired output dk of n minus yk of n. Here n is nothing but n iterations, k is nothing but kth neuron. Ek of n is equal to dk of n minus yk of n. Now the error energy to be minimized is, the corresponding error energy is nothing but E of n is equal to half ek square of n. I can directly give that ek of n need to be 0, but we need to differentiate and we need to equal to 0, right? That's why half and ek square of n, if differentiate that, your error will be equal to 0. To minimize the error, we need to differentiate and equal to 0. That's why that half and ek square of n is coming here. By differentiating that and equating it to 0, your error will be minimized. The corresponding condition or error will be minimized, right? Anywhere in any minimization problem, we will differentiate and equate to 0, then you will get the condition, right? That's what here we are doing. So if you do that actual error function, it is ek of n. That's why here we have taken that of ek square of n as an error energy function. This error energy need to be minimized now. The minimization of error energy leads to a learning rule, which is called delta rule or Windrow-Hoff rule. Based on this rule, the corresponding error del wkj of n, error is nothing but del wkj of n is equal to neta into ek of n into xj of n. So here neta is nothing but learning parameter. Delta wkj of n is nothing but the kj represents n is nothing but delta wkj of n. That n is nothing but iterations, number of iterations. What is k? K is nothing but output neuron, kth neuron, that is nothing but kth neuron. J is nothing but corresponding jth input vector. That's why wkj of n, which is equal to neta into ek of n, the corresponding kth neuron error, into xj of n, corresponding input at the input from the jth vector. So it needs to be error and the corresponding input at the jth vector need to be multiplied with the learning parameter to get that corresponding change in error, change in weights. The updated now, once if you get that delta wkj of n, then the updated weight is nothing but wkj of n plus 1. The updated weight, next level weight is nothing but wkj of n, previous weight, plus corresponding error delta wkj of n. So this gives the updated weight. This weight will contribute towards the reduction or minimization of the error. Like this process is continuous, so it will continue either the change in weight delta wkj of n may be plus or maybe minus. It depends on the error variation. If error is increasing means it will go in other direction. If error is decreasing means it will go in other direction. The trends towards that either increase or decrease. That's called trends. Either it can add to the previous weights or it can subtract from the previous weights. So that decides based on the error variation, error trends. The same thing can be represented with the signal flow graph as represented in this diagram. When what we have seen in the block diagram, the same thing here I have represented. We see here x1, x2, xj of n and so on, xm of n are the input vectors. And the corresponding weights are wkn, wk2 and so on, wkj and so on. Wkm are the corresponding weights of the connection links. And k is the output neuron, the corresponding output of the neuron is nothing but vk of n. The corresponding activation function is pi. Here as no need to represent any function, simply that pi of dot represent the activation function. And the overall output is nothing but yk of n. That yk of n need to be subtracted from the desired output dk of n, right? That's why the corresponding minus 1 is represented in the signal flow graph direction. So now ek of n is the error because of that minus 1. Now what is ek of n? Ek of n is equal dk of n minus yk of n. So that error need to be adjust the corresponding connection weights of the kth neuron. output neuron. It is nothing but WK1 to WK2 and so on WKM. Those weights need to be adjusted because of that error. So here, like I represented jth input vector of kth neuron, WKJ, corresponding weights, WKJN, how many number of iterations required, N is the number of iterations required to minimize that error. You can perform number of times, right? That's why WKJ of N. KJ represents the kth neuron, the corresponding connection link is nothing but jth vector. So here, that's what I represented. The input signal xj and induced local field are net output Vk of n. Output of the corresponding kth neuron is Vk of n, and the corresponding input signal is xj, or the presynaptic and postsynaptic of the jth synapse. Corresponding jth synapse of the neuron K. One is input vector, that is nothing but xj, and the corresponding output is nothing but Vk of n. So it is closed loop feedback system. What we have seen, the stability depends on the feedback parameter neta, which is learning rate parameter. Here learning rate parameter is very important. Even in the PID controller also, how you choose the PID values, either by auto tuning or manual tuning. The PID values will contribute or will affect the performance of the feedback system, right? Here likewise, the neta, learning rate parameter, decides the whether error need to be converged or diverged. We need to choose that error value, that learning rate parameter properly to minimize that error value. That's why that selection of neta is very important. So the selection of neta is to be done very carefully for the stability and accuracy of the system. Here these two main functions or main parameters decides based on that learning rate parameter neta. One is stability, another one is accuracy of the system. So those two required for any system, right? So those two depends on that learning rate parameter. Stability and accuracy of the system depends on the learning rate parameter. So hence it needs to be selected properly. So this is all about the learning rate, learning rule, and credit assignment problem, and the limitations of the single layer perceptron. Thank you all.